Now that we know what it means for an ideal to be principal and what it means for an ideal to be finitely generated, the goal of this video is to introduce a couple of key examples. And first, we'll talk about an example of an ideal that is not principal. So we saw that in any ring, the trivial ideal and the entire ring R are principal. This is, remember, we're assuming that the ring R contains a multiplicative identity. And then we also saw that in Z, our next kind of like simplest example to work with, every ideal is principal. So to look for an ideal that's not principal, we have to go somewhere else. So let's look in Z bracket X for R and I to be the ideal generated by 2 and X. So what is this ideal? Like, what do its elements look like? R is a commutative ring. So we're taking finite sums of elements of the form something in the ring times 2 plus something in the ring times X. And then if we repeat some of those elements, we can use the distributive law to group them together. So in the end, this ideal I just consists of everything that can be written as 2 times some polynomial in Z bracket X plus X times some polynomial in Z bracket X. Okay, again, this is another instance where we're seeing that this is the same thing as the sum of the ideal generated by 2 and the ideal generated by X. So what's in here? Well, X times Q of X has constant term equal to 0. Because all of the non-zero terms have degree at least 1, because there's a factor of X. 2 times P of X, all of the coefficients are even. So in particular, the constant coefficient of 2 times P of X plus X times Q of X is the constant coefficient of 2 times P of X, and it's even. So we can see that this ideal consists of all polynomials in Z bracket X with even constant term. And okay, why is this an ideal? We already saw this ideal in the last lecture. We saw that it was the kernel of a ring homomorphism that came from taking our polynomial in Z bracket X, sending it to its constant term. That was a ring homomorphism from Z bracket X to Z. And then we have a homomorphism which goes from Z to Z mod 2Z, where you reduce mod 2, 0 for even numbers, 1 for odd numbers. Okay. And the point here is that I is not a principal ideal. How are we going to show that this is not principal? Often when you want to show an ideal is not principal, the idea is proof by contradiction. You suppose that the ideal is principal. You choose some element so that your ideal is the ideal generated by that element. And then you show that there's a problem, that there's in fact no element that satisfies all the things that need to be satisfied. So, okay. Let's suppose I is equal to the ideal generated by A of X for some polynomial A of X in Z bracket X. So 2 is in the ideal generated by A of X. So what does that mean? When are you in a principal ideal in a commutative ring? Well, that means that there exists some B of X in Z of X so that 2 is equal to the product of A of X times B of X. So let's look at the degree of the polynomials on both sides here. The degree of A of X times B of X is the sum of the degree of A plus the degree of B. And if that's equal to the degree of 2, well, as a polynomial in Z bracket X, 2 has degree 0. So what does that mean? We're adding up 2 non-negative integers and getting 0. So they both have to be 0. So the degree of A of X is 0 and the degree of B of X is 0. So that means A of X is a constant polynomial. So it must actually just be some element in Z. And B of X is a constant polynomial also. So I'm going to stop writing A of X and B of X and just write A and B. So what's true? A times B equals 2. So what does that mean? These are 2 integers that multiply to 2. So A is plus or minus 1 and B is plus, or sorry, A is plus or minus 1 or it's plus or minus 2. If you pick your value of A, you see what B has to be. All right, well, let's just go through cases. If A is plus or minus 1, then the ideal generated by A of X, which is the ideal generated by A, is all of Z bracket X. It's not this ideal I. So this ideal is too big. So A can't be plus or minus 1. So what if a was plus or minus 2, the only other possibility? Well, then we'll see that x is not in the ideal generated by a. So I'm just going to write 2 for a now. If a is minus 2, the argument's exactly the same. But for notation, it's a little easier. So suppose x is in the ideal generated by 2. What does that mean? There exists a polynomial b of x in z bracket x where x equals 2b of x. That means that there's some polynomial with integer coefficients where you multiply by 2 and you get x. But what happens when you multiply a polynomial by 2? You're multiplying all the coefficients by 2. So that would mean that the x coefficient of b of x would have to be 1/2. So there are no solutions. Like such a b of x doesn't exist. So x is not in the ideal generated by 2. Similarly, it's not in the ideal generated by -2. So none of the 4 possibilities for a are possible. So there is no polynomial a of x in z bracket x with I equal to the identity generated by a of x. So we have shown that in fact, the ideal generated by 2 and x is not a principal ideal in z bracket x. So let me point something out before moving on. When we're solving this equation x equals 2 times b of x, there's no solution in z bracket x, but there is a solution in q bracket x. You could just set b of x be equal to 1/2 x. So it's really important when you go through these kinds of arguments to remember what ring you're in, like remember where you live. The ideal generated by 2 and x in z bracket x is not principal, but the ideal generated by 2 and x in q bracket x is principal. The ideal generated by 2 and x contains the element 1/2 times 2, which is 1. That's an element of q bracket x. And once you contain 1, you contain the whole ring. So in q bracket x, the ideal generated by 2 and x is principal. It is all of q bracket x. It's the ideal generated by 1. So this is a good example to keep in mind. This kind of thing will come up more when we talk more extensively about polynomial rings. So I'll pause and erase, and then I'll do another sort of similar example, but from a different perspective, building on material that we talked about in the last lecture. Now let's talk about the same ring and ideal, but from a different perspective. Let's take z bracket x and this ideal generated by 2 and x. And now let's ask, what is the quotient ring R mod I? And in the last lecture, we saw the answer to this. We saw that R mod I is isomorphic to z mod 2z. And we saw this by seeing that I was the kernel of a ring homomorphism that was the composite of 2 nice ring homomorphisms. And then we applied the first isomorphism theorem to conclude. So there's another way to do this that uses 2 of the other isomorphism theorems that we talked about at the end of the last lecture. And I wanted to wait to introduce this until we had introduced this ideal generated by 2 elements notation. Okay, the third isomorphism theorem says, well, okay, we want to understand R mod I. Let's take some ideal j that's contained in the ideal I. So R mod I is isomorphic to R mod j mod I mod j. So it's the sort of like cancel like your fractions one. So R mod I is isomorphic to z bracket x mod the ideal generated by x, that's playing the role of our j here, mod the ideal generated by 2 and x mod the ideal generated by x. And we know what this first thing is, z bracket x mod the ideal generated by x. What do the cosets look like in this quotient ring? They're exactly identified with the constant terms of whatever polynomial. So this ring, quotient ring, is isomorphic to z. So now the question becomes, what is the ideal generated by 2 and x mod the ideal generated by x? And here it's going to be useful to switch a little bit from the notation of the ideal generated by 2 and x to the sum of the ideal generated by 2 and the ideal generated by x. We've already seen that these are the same thing. What's the point of doing that? Well, now this question is in a form where we can apply the second isomorphism theorem. So let's take the ideal generated by 2 and x mod the ideal generated by x. That's the same as the sum of the ideal generated by 2 plus the ideal generated by x mod the ideal generated by x. And by the second isomorphism theorem, this is, okay, a plus b, or 2 ideals modulo b, is isomorphic to a modulo a intersect b. So the ideal generated by 2 mod the intersection of the ideal generated by 2 and the ideal generated by x. So now we have to understand this intersection. So what does it mean for a polynomial to be in the ideal generated by 2 and the ideal generated by x? Well, a polynomial is in the ideal generated by x exactly when its constant term is 0. That's what it means to be x times something. And you're in the ideal generated by 2 if all your coefficients are even. So a polynomial is in here if and only if its constant term is 0 and all the other coefficients are even. But that's the same thing as being divisible by the polynomial 2x. So if you just think about it. So that means that this intersection is the principal ideal generated by 2x. So, okay, so now the quotient that we care about is the ideal generated by 2 mod the intersection of the ideal generated by 2 and the ideal generated by x. And that's the same as the ideal generated by 2 mod the ideal generated by 2x. And this is easier to understand by just seeing, like, what does an element of this quotient look like? So elements of this quotient look like polynomials, all of whose coefficients are even. That's what it means to be in the ideal generated by 2. But 2 of them lie in the same coset here if they have the same constant term. So you take a polynomial with all even coefficients. When can you write p of x equals q of x plus 2x times some polynomial, all of whose coefficients are even? Okay. Yeah, okay, so what do the coset representatives look like? They look like a copy of 2z. So what does that mean? That means that this quotient ring that we care about from the beginning, this first piece is isomorphic to z, and this second piece, this quotient here, is isomorphic to 2z. So in the end, this quotient is isomorphic to z mod 2z, which is what we knew from last time, but here we're getting at it in a different way. So what's going on? You could change this 2 to some other prime number. And more generally, z bracket x mod the ideal generated by p and x is isomorphic to z mod pz. All right, so I'll pause and erase, and then we'll do one other type of example. We'll see an ideal in a ring that is not finitely generated. For the last example of this lecture, let's recall that an ideal of R, is finitely generated if I is equal to the ideal generated by A for some finite subset A of R. So let's take R to be equal to Q adjoin x1, x2, x3. It's a polynomial ring in infinitely many variables. So this is not an example we have seen yet, but it's a good one to know and keep in mind. This is a polynomial ring in countably many variables. What does an element of this ring look like? Well, elements are polynomials. They're finite sums of terms like c, some constant in Q, times xi1 to the e1, times xi2 to the e2, times xin to the en. So it's like having a polynomial in 2 variables or 3 variables or 10 variables or 1,000 variables, except there's infinitely many different variables xi, but a polynomial is still a finite sum of terms, and each term only involves finitely many of these infinitely many variables. Okay, so what's the ideal? Well, okay, so first I should say it's a good exercise to check that this really is a commutative ring. It has an identity, which is just the element 1 inside of Q, the constant polynomial. How do you multiply these things? You multiply just like you multiply polynomials. You multiply together, you expand all the terms, and then you combine terms that have the same exponents, the same variables. So let's take the ideal generated by x1, x2, x3 by these countably many variables. And the claim is that I is not finitely generated. Okay, just like arguments that show an ideal is not principal, to show an ideal is not finitely generated, usually these go by contradiction. So let's suppose that I is finitely generated, that there's finitely many polynomials f1 up through fm in this ring R, so that I is the ideal generated by this finite set. So that there is some finite subset A of this ring for which I is the ideal generated by those elements. And the key thing in this argument is that each of these fi's is a polynomial, meaning it only has finitely many non-zero terms. And every one of those terms only involves finitely many of these infinitely many variables. Maybe f1 is a polynomial that has 1,000,000 terms, and each of those terms involves 1,000,000,000 different variables. But still, altogether, the total number of xi's that could show up somewhere in one of those non-zero terms is at most 1,000,000 times 1,000,000,000. So there's only finitely many of these variables that show up in f1. Similarly, f2 up through fm. If you take the union of all of these polynomials and you take all of the terms, non-zero terms in these polynomials, only finitely many out of these infinitely many variables can possibly show up in a non-zero term. Okay, so what are we going to do? We're going to take xr to be one of these x1, x2 up through x, this set of variables corresponding to positive integers. We're going to take one that doesn't show up in any non-zero term of any of these polynomials. And now the claim is that xr cannot be in the ideal generated by f1 up through fm. But xr is definitely an I. So that's going to contradict the assumption that I was generated by f1 up through fm. Okay, so now, what does it mean for xr to be in this ideal? It means that there are polynomials a1 up through am in R such that xr is equal to a1 f1 plus a2 f2 plus am fm. And now the key thing is that the xr coefficient on the left is 1. What is it on the right? Well, none of these fi's has an xr in it anywhere. So anywhere you're picking up an xr has to be from one of these polynomials ai. So you can zoom in and like just look at the ar coefficient of each of these a1, a2 up through am. And you could see like, well, you could pick up an xr, like if a1 had a term that looked like xr and f1 had a constant term of 1. But you're still going to run into a problem here. So I'm going to leave the details of the rest of this as an exercise because this isn't the kind of thing that we're going to need for a little while. But since we introduced the concept of what it means for an ideal to be finitely generated, I definitely wanted to show you an example of an ideal that is not finitely generated.